Good afternoon. Welcome once again to this group, that is PG semester second CC4 group. In continuation of the previous class, today we will study the entropy change of mixing of two ideal gases. Suppose two ideal gases A and B having Na and Nb moles are mixed at constant temperature capital T under a constant pressure capital P. Before mixing, their entropies may be given as their entropy may be given as SA, entropy for A, SA is equal to Na into CPLNT minus RLNP plus IA, that we have read in previous class. And SB will be equal to NB into CP LNT minus RLNP plus IB. NB is the number of moles of B, N is number of moles of A, Cp is the heat capacity at constant pressure of B, CPB right now, and this is CPA, heat constant, a specific heat at constant pressure of B, and Cpa is the specific heat of A. P is pressure. This expression was derived in the previous class. When we mix these gases A and B, after mixing, now come after mixing, the total pressure P may be expressed as sum of partial pressure of A and B, that is P equal to PA plus PB from Dalton's law of partial pressure. And entropy of mixing are in a similar way SAM. M denotes for mixing. SAM is equal to Na into Cpa ln Cpa ln minus R ln here Pa in terms of partial pressure ln Pa plus Ia. And SBM means entropy of B after mixing will be equal to NB into CPB ln T minus R ln here PB plus IB. This is after mixing. Therefore, change in entropy after mixing, change in entropy after mixing will be given by delta S M. This will be equal to entropy, sum of entropy of A and B after mixing minus sum of entropy of A and B before mixing. That is SAM plus SBM minus SA plus S. Now put the value SM, SBM and SA and SB. SM, Na, into CPA ln T minus R ln PV plus IB plus this NB into CPB ln T minus R ln PB plus IB. This is the value SAM, this is SM and this is SBM. Minus SA plus SB minus SA NA CPA ln T minus R ln P plus IB plus NB CPB ln T minus R ln P plus IB. Now simplify this. After simplification, we will get delta SM is equal to minus Na R ln Pa or ln Pa plus Na R ln P minus NB R ln PB plus NB R ln P. Here this IB CK, sorry, here this is IA and IA. After minus, this will be cancelled. Now NAR LNP, this will be equal to take common Na minus N, take common minus N R. From this will be equal to LNPA minus LNP, and from these two terms, when we take common NVR, we will get LNPV minus LNP. So this will be written as minus Na into R, and LNPA minus LNP is equal to, this will be equal to LNPA by P, and minus NBR, this will be equal to LNPB by P. From logarithmic formula, this is entropy change after mixing. Now this term PA by P is equal to mole fraction. Mole fraction, from definition of mole fraction, we know the partial pressure of a component divided by total pressure is called mole fraction of that component. So this is PA by P is mole fraction of A in the gaseous mixture. We know, write down, mole fraction of A, which is denoted by the symbol this, chi A, chi, pronunciated as chi, chi A. Chi A is equal to PA divided by P, and mole fraction of B, which is denoted by chi B, is equal to PB divided by P, partial pressure of P divided by total pressure. Putting this value to the expression, we will get, therefore delta Sm is equal to minus Na into R, Na into R into ln PA by P is equal to chi A, ln chi A minus NAR into ln chi A minus NB R into ln chi b. Again, in terms of partial pressure, the mole fraction is Pa by P, but in terms of number of moles, this is equal to mole fraction of mole number of moles of A divided by total mole. So mole fraction of A, chi A is equal to Pa by P, which is equal to Na by N. Na is the number of moles of A and a small n is the total number of moles in the mixture. Similarly, mole fraction of B in terms of mole is equal to Nb divided by N, which is equal to chi B. Number of moles of B divided by total mole. So, we may write from this relation since chi A is equal to Na by N also, therefore Na may be written as N into chi A. N into chi A. Similarly, we can write chi B is equal to Nb by N, therefore Nb equal to N into chi B. Putting this value of Na and Nb in this expression, putting the value of Na and Nb in the above equation, we get delta Sm is equal to minus N into chi A, N into chi A into R into ln chi A minus, and Nb is equal to N into chi B into R into ln chi B. take common nr delta Sm is equal to minus nr chi a into ln chi a minus chi b into ln chi b. This is expression for the entropy change of mixing of two ideal gases A and B. For two gases, if several gases are mixed, suppose mixture containing I component, this equation may be written as this is entropy of mixing for two gases A and B. For mixture of ideal gases having I component, we may write one delta SMI, M for mixture, I for component, change in entropy of I component mixture or mixing of I component change in entropy will be equal to minus nr summation of product of mole fraction into logarithm of mole fraction of all the components. Here correct this will be plus, minus is taken common in this expression. So nr will equal to summation of mole fraction of each component up to I into ln mole fraction of each component, and this is summation is component 1 to I component. Equation 2, equation 1 is the change in entropy of mixture of two ideal gases A and B, and equation 2 is the expression for the mixture of ideal gases we may summarize that total change from these two expressions we may sum up the total change, that is the total change in entropy of mixing of 1 to I, this is 1 to I ideal gases is equal to minus nr into multiplied by sum of product of mole fraction of each component multiplied by logarithm of mole fraction of each component. Thus equation 1 and equation 2 are the total entropy change of mixing of various one is for two ideal gases and equation 2 is for I ideal gases. Now we make the following conclusions from the above equation. Conclusion, what is conclusion? Delta S mixing is equal to minus R summation of chi I ln chi I. Case 1, this expression is independent of temperature. Thus we may say change in entropy of mixing is independent of temperature. Means it does not depend upon the change of temperature. And second conclusion is that a mole fraction of any component, suppose chi I, for any component, this is always less than 1. So if chi I is less than 1, then delta S mixing will be always positive. Positive. Change in entropy of mixing is positive, means mixing of gases is accompanied by increase in entropy. That is, mixing of gases is accompanied by increase in entropy. This was the last case. Come to a sum related to this expression. We may ask, the question may be asked like this: calculate the entropy change of mixing of 0.2 moles of a gas and 0.6 moles of another gas, moles of another gas at 25 degrees Celsius or any temperature, assuming that the gases behave ideally. This type of question may be asked. Now solve this question. Solution of this question is, we know, at first write the entropy change for mixing formula. change in entropy of mixing of two gases minus R summation chi I for I component chi I into ln chi I. For two components, from this formula we can calculate the entropy change of 2, 3, 4, 5, etc. mixing of ideal gases. For two components, this formula may be written as delta Sm equal to minus R chi 1 for first gas, chi 1 ln chi 1 plus other gases. Suppose this is gas number 2, chi 2 into ln chi 2. Now, from question, what is given? 0.2 moles of a gas. For first gas, the number of moles is 0.2. Given from the question. Number of moles N1 is equal to 0.2 moles and N2 for other gas number of moles is 0.6 moles. Now calculate the mole fraction. So therefore mole fraction chi 1 for first gas will be equal to number of moles of first gas divided by total number of moles N1 plus N2. This will be equal to 0.2 divided by 0.2 plus 0.6 equal to 0.2 divided by 0.8. This will be equal to 0.25. 1 by 4, 0.25. Similarly, chi 2 mole fraction of other gas, number of moles of second gas divided by total number of moles. This is equal to the value of N2 is 0.6. 0.6 divided by 0.2 plus 0.6 This is equal to 0.6 by 0.8. This will be equal to 0.75. Now put this value of n1 and n2, sorry, chi1 and chi2 in this equation. Therefore, delta Sn is equal to minus R equal to chi1 0.25 ln 0.25 plus chi2 0.75 into ln 0.75. The value of R in SI unit is 8.314. This is equal to minus 8.314 joule प्रति Kelvin प्रति mole, and this is equal to ln. Convert it into in natural log, log base 10, convert it. This is 0.25 into 2.303. This is the relation between natural log and log to the base 10 log 0.25 plus 0.75 into 2.303 log to the base 10 0.75. Here R is equal to 8.314 joule प्रति Kelvin per mole. Now simplify. Delta Sm will be equal to minus 8.314 into 2.303 into 0.25 log 0.25 plus 0.75 into log 0.75. This value comes after simplification 4.678 joule per Kelvin per mole. This is entropy of mixing of two gases per mole. Entropy of mixing of two gases formula. In this way, entropy is finished. In next class, we will study the other topics, free energy. Thank you.